Dear students, welcome. This is our third class on vector calculus. Today we shall discuss about gradient of a scalar point function. The gradient of a scalar point function is a vector point function. Before that, we must define the partial derivatives of vectors. Partial derivatives. Of vector. Let R vector is a vector function of three scalar variables. That is, R vector is a vector function of three scalar variables. X, Y, Z. Of three scalar variables x, y, z. Then the partial derivatives of the vector R vector with respect to x is defined as delta R vector by delta x equal to limit as delta x tends to 0, delta x at factor x plus delta x yz minus xyz minus xyz. If the limit exists. Thus, delta R vector by delta x is nothing but the ordinary derivative of R vector with respect to x. R vector with respect to x, provided that the other scalar, the other variables y and z are regarded as constant. Partial derivatives of x, partial derivatives of R vector with respect to x, treat the other variables y and z as constant. Similarly, we can define delta R vector by delta y, delta R vector by delta z. Similarly, we can define this. Now, let me define higher order partial derivatives. Higher order partial derivatives. The second order differentiation of this you may write like this. If you differentiate del R del x with respect to x partially, then you will get the second order differentiation. Like that, delta to delta y square, you may write delta delta y, delta R delta y, delta to R vector delta z square, delta delta z, delta R vector by delta z. Delta to R vector delta x delta y. It is nothing but delta delta x delta R delta y. delta 2 r vector delta z delta x del del z delta r vector by delta x, etc. We can find the second order differentiation partially like this. Third order differentiation, if you want to find the third order differentiation, delta cube r vector by delta x cube, just delta delta x or delta 2 r vector by delta x square, etc. like that. Differentiate this partially with respect to x. In this way, we can find the higher order partial differentiations. If r vector has continuous partial derivatives of second order at least, then delta 2 r vector delta x delta y, this is equal to delta 2 r vector delta y delta x. This means first you may differentiate partially r vector with respect to y, then differentiate del r del y with respect to x. The result will be the same if you differentiate first r vector with respect to x, then you differentiate this with respect partially with respect to y. This means first time this. Now let us define a symbol operator. Let us define an operator. I am going to define a operator. This operator is called del or nabla. It is operator. Operator del or nabla. Operator del or nabla. We define this operator is equivalent to I cap delta delta x plus j cap del del y plus k cap del del z, or you may write del del x I cap plus del del y j cap plus del del z k cap. You may write like this also. You may write like this. Now I am going to define you the gradient of a scalar point function. Gradient of a scalar point function. Let f x y is defined and is differentiable. And is differentiable at each point x, y, z in a certain space, certain region in space. Let f is defined and is differentiable at each point x, y, z in a certain region in space. Then the gradient of f, then the gradient of f is defined as f, of course it is a function of x, y, z, scalar point function, as the gradient of f equal to I cap del del x j cap del del y plus k cap del del z. F which is equal to I cap delta f by delta x plus j cap delta f by delta y plus k cap delta f by delta z. It is defined as this. Therefore, gradient of a scalar function is a vector function. Therefore, the gradient of a scalar function f is a vector function whose components are delta f by delta x, delta f by delta y, and delta f by delta z, and delta f by delta z. Gradient f is generally denoted by, we have already denoted this, this gradient f is denoted by, of f is denoted by, we have already denoted this, gradient of f or this notation f, gradient of f or this notation f. It is nothing but I cap delta f by delta x plus j cap delta f by delta y plus k cap delta f by delta z, like this. Perhaps you have understood this. Now, theory. The gradient of the sum of two scalar functions is equal to the sum of the gradient of the scalar functions. Scalar functions. This is theorem number, I am writing it as number 1. This is number 1. Let f and g be two scalar point functions. Functions of x, y and z. Be two scalar point functions of x, y, z. F and g are two scalar point functions of x, y and z. Then gradient of f plus g, this is equal to the gradient of f plus g, this is equal to I cap del del x, j cap del del y plus k cap del del z of f plus g. This is equal to I cap del del x of f plus z plus j cap del del y of f plus z plus k cap del del z of f plus z. By the definition, you may write like this. This is nothing but I cap delta f by delta x plus delta z by delta x plus j cap delta f by delta y plus delta z by delta y plus k cap delta f by delta z plus delta z by delta z. This is equal to I cap delta f by delta x plus j cap delta f by delta y plus k cap delta f by delta z plus, you may write like this, delta z by delta x plus j cap delta z by delta y plus k cap delta z by delta z plus k cap delta z by delta z. delta z by delta z. You may write it as directly. You may write it as gradient of f. Directly you may write gradient of f. Or for the first time I am writing here f plus or this is equal to nabla f plus nabla c. This is equal to gradient of f plus gradient of z. Gradient of z. You may not write this step also. You may not write directly from this step. You may write it is gradient of f plus this is gradient of z. Gradient of z. Thus, gradient of f plus z. This is equal to gradient of f plus gradient of z. Similarly, we can prove that. Gradient of f minus z. This is equal to gradient of f minus gradient of z. Similarly, we can prove this. That is gradient of f minus z. This is equal to gradient of f minus gradient of z. Gradient of z. This operator is a vector operator. I cap delta delta x plus j cap delta like this. Theorem we have proved the theorem number 1. Theorem number 2. Theorem number 2. The necessary and sufficient condition. And sufficient condition. The necessary and sufficient condition. The necessary and sufficient condition for a function f to be constant, a constant function, is that gradient of f equal to 0. Gradient of f equal to 0. Gradient of f is equal to 0. Now, let f of xyz be a constant function. Constant function. I am writing here xyz. You may write since it is a constant function, the differentiation of f with respect to xyz should be equal to 0. It is a constant function. Therefore, delta f by delta x equal to 0. Del f by del y equal to 0. Del f by del z. This is also equal to 0. Since it is a constant function. Therefore, gradient of f, this is equal to the gradient of f equal to I cap delta f by delta x plus j cap delta f by delta y plus k cap delta f by delta z. This is equal to I cap 0 plus j cap 0 plus k cap 0. I am very sorry, gradient of f, this should be a vector 0. It is a vector notation because gradient of a scalar function is a vector function. Therefore, we should write the vector sign here. This is equal to the 0 vector. Gradient of a scalar function is a vector function. Therefore, we should write vector sign 0 vector. We should write 0 vector in place of 0. Conversely, suppose that therefore gradient of f equal to 0 vector. If it is a constant function, then conversely suppose that gradient of f vector equal to 0 vector. This means I cap delta f by delta x plus j cap delta f by delta y plus k cap delta f by delta j equal to 0 vector. It can be written as 0 a cap, 0 j cap, 0 k cap. Equating the coefficients of I cap, j cap, k cap we get. Equating the coefficients of I cap, j cap, k cap we get. Equating the coefficients of I cap, j cap and k cap we get. Equating the coefficients of I cap, j cap and k cap we get delta f by delta x equal to 0, delta f by delta y equal to 0 and delta f by delta z equal to 0. Equating the coefficients of this equal to 0. That is, f is independent of x, y and z. That is, f is independent of x, y and z. Therefore, f is a constant scalar. Constant scalar. Conversely, we have proved this one. Now, theorem number 3. Let us come to the theorem number 3. Perhaps you have noted down. Perhaps you have noted and you have understood this. Theorem number 3. Theorem number 3. If f and g are two constant scalars, if f and g are two constant scalars, scalar point functions, then gradient of fg equal to f of gradient of g plus g of gradient of f. You may write like this. That is, the gradient of fg equal to f gradient of g plus g gradient of f. You may write like this. We have to prove this one. We have to prove this one. Proof. Gradient of fg equal to I cap delta delta x plus j cap delta delta y plus k cap delta delta z of fg. Delta delta z of fg. This is equal to I cap delta delta x of fg plus j cap delta delta y of fg plus k cap delta delta z of fg. This is equal to I cap the differentiation of fg per se with respect to f delta z by delta x plus g delta f by delta x. You may write like this plus j cap f delta z by delta y plus g delta f by delta y plus k cap f delta z by delta z plus g delta f by delta z. Delta f by delta z. You may write like this. You may write in this way. You may write like this. This is equal to f I cap delta z by delta x. Here it is also an f plus j cap delta z by delta y plus this f k cap delta z by delta z plus z. Now z I cap delta f by delta x plus j cap delta f by delta y plus k cap delta f by delta z. Delta f by delta z. This is equal to f. It is nothing but the gradient of z. It is nothing but gradient of z plus z. It is nothing but gradient of f. Thus, gradient of fz equal to f gradient of z plus z gradient of f. Z gradient of f. Or you may write in this way also, gradient of fz is equal to f of gradient of z plus z of gradient of f. Z of gradient of f. Now, it is very easy. Just treat gradient as the differentiation. First function, differentiation of the second function, plus second function into differentiation of the first function. In place of differentiation, you may write gradient. You may write gradient. Now I am going to give you a corollary here. If C is constant and f is a function, f is a scalar point function, of x, y and z, then gradient of CF equal to C gradient of f plus f gradient of C. F gradient of C. C gradient of f plus f gradient of C. Now, gradient of C equal to I cap delta C by delta x plus j cap delta C by delta y plus k cap delta C by delta z. Now C is constant. Now you see C is constant, therefore the differentiation will be equal to 0. C is constant. This means delta C by delta x equal to 0, delta C by delta y equal to 0, delta C by delta z will be equal to 0. Will be equal to 0. Therefore, the gradient of CF will be equal to C into gradient of F. Simply gradient of F. This means the C can be taken outside the gradient. In case of differentiation, the differential coefficient of the product of a constant and a function, this is equal to the product of the constant and the differentiation of the function. Like this, the gradient of the product of a constant and a function, this is equal to the product of the constant and the gradient of the function. Like that. This is very easy. Theorem number 4. I am going to give you the theorem number 4. I am going to give you the theorem number 4. If f and g are two scalar point functions, if f and g are two scalar point functions of x, y, z, then the gradient of f divided by z equal to z square z gradient of f minus f gradient of z. That is, in this way also you may write gradient of f by z. This is equal to z gradient of f minus f gradient of z. You may write like this, divided by z square, provided z is not equal to 0. provided g is not equal to 0. Provided g is not equal to 0, you may write like this. It can be also easily proved. Now, proof of this. Gradient of f by z equal to I cap delta delta x plus j cap delta delta y plus k cap delta delta z f by z. This is equal to I cap this is equal to I cap z delta f by delta x minus f delta z by delta x z cap z square z delta f by delta y minus f delta z by delta y plus k cap. Here also z square z delta f by delta z minus f delta z by delta z. You may write in this way. Now, this is equal to 1 by z square. Take it as common. Take it as common. I cap z delta f by delta x minus f delta z by delta x plus z cap z delta f by delta y minus f delta z by delta y plus k cap z delta f by delta z minus f delta z by delta z delta z by delta z. This is equal to 1 by z square. Now take z common. 6 terms are there. Z is common. Take z common. You may write I cap delta f by delta x plus z cap delta f by delta y plus k cap delta f by delta z minus, now f common. In the bracket you will get I cap delta z by delta x plus j cap delta z by delta y plus k cap delta z by delta z plus k cap delta z by delta z. This is equal to 1 by z square. Z, it is nothing but gradient of f minus f, it is nothing but gradient of z. Gradient of z. This is equal to, you may write z square. In the denominator z square, in the numerator z into gradient of f minus f into gradient of c, minus f into gradient of c, just like this. Thus as differentiation. The differentiation of the coefficient of two functions equal to denominator into differentiation of the numerator minus numerator into differentiation of the denominator divided by the square of the denominator. In this case also, in case of differentiation, you should write gradient. Denominator into gradient of the numerator minus numerator into gradient of the denominator divided by square of the denominator, like this. Perhaps you have understood this. It is very easy. Now, the gradient of, prove that, the gradient of f to the power n, f to the power n. What is this? This is equal to the differentiation of x to the power n will be n into x to the power n minus 1, n into f to the power n minus 1. If you are differentiating with respect to x, suppose it is a function of y, then you will write dy by dx here. In a similar way, the gradient of f to the power n into f to the power n minus 1, the gradient of f, the gradient of f, the very simple proof. Gradient of f to the power n, this is equal to I cap delta delta x plus j cap delta delta y plus k cap delta delta z of f to the power n. I cap delta delta x of f to the power n plus j cap delta delta x of f to the power n plus k cap delta delta z delta delta y. This is delta delta z of f to the power n. This is equal to I cap n f to the power n minus 1 delta f by delta x plus j n f to the power n minus 1 delta f by delta y plus k cap n f to the power n minus 1 delta f by delta z. This is equal to n f to the power n minus 1 common, take it common, I cap delta f by delta x plus j cap delta f by delta y plus k cap delta f by delta z, delta f by delta z. You see, this is nothing but gradient of f. n f to the power n minus 1, this is nothing but gradient of f. Or you may write this is equal to this is, you may write in this way also, the same thing, gradient of, right? Prove that. Suppose let R vector, the magnitude of the vector is R. Suppose magnitude of the vector R vector is equal to R. Not only that, and R vector is equal to x I cap plus y j cap plus z k cap. Suppose this R vector is equal to x I cap plus y j cap plus z k cap, and magnitude of this vector R vector is equal to R. This means magnitude of this vector will be equal to root of R, x square plus y square plus z square. This means R square equal to x square plus y square plus z square. Differentiating with respect to x partially, you will get twice R delta R by delta x. This is equal to twice x. Twice R delta R by delta x equal to twice x. Differentiate this partially with respect to x. This means delta R by delta x equal to x by R. Similarly, delta R by delta y equal to y by R, delta R by delta z equal to z by R. Similarly, you may write in this way also. Similarly, now gradient of, suppose 1 by r. What will be this? Equal to I cap delta delta x of 1 by r plus j cap delta delta y of 1 by r plus k cap delta delta z of 1 by r, like this. Or you may write it as I cap minus r to the power minus 2 delta r by delta x plus j cap minus r to the power minus 2 delta r by delta y plus k cap minus r to the power minus 2 delta r by delta z. You may write in this way also. Minus r to the power minus 2. You may take it as common. I cap delta r by delta x plus j cap delta r by delta y plus k cap delta r by delta z. You may write like this. This is equal to minus r to the power minus 2 I cap. It is nothing but x by r plus j cap y by r plus k cap z by r, k cap z by r. Or here you may write this is equal to minus r to the power minus 2 x I cap plus y j cap plus z k cap. This is equal to minus r to the power minus 3 r vector. R vector. This is equal to minus 1 by r cube r vector. You may write in this way. Anything mistake? 1 by r to the power minus 1 minus r to the power minus 2. Yes, right. This r will be equal to r to the power minus 3. Yes. You may write like this. Therefore, gradient of 1 by r equal to minus 1 by r cube r vector. Gradient of r is equal to this. 1 by r cube r vector. Now, gradient of f equal to gradient of a function of r equal to I cap delta delta x of fr plus j cap delta delta y of fr plus k cap delta delta z of fr delta delta z of fr. You may write like this. This is equal to I cap f dash r with respect to r differentiation. F dash r delta r by delta x plus j cap f dash r delta r by delta x plus k cap f dash r delta r by delta x. You may write in this way also. This is equal to f dash r I cap delta r by delta x plus j cap delta r by delta it is I am sorry, it is y and it is z. It is x I cap delta r by delta y plus k cap delta r by delta z. This is equal to f dash r I cap. It is nothing but x by r plus j cap. It is nothing but y by r. It is k cap. It is nothing but z by r. This is equal to f dash r divided by r x I cap plus y j cap plus z k cap. This is equal to f dash r divided by r vector. Gradient will be again always r vector. Thus, corollary. You may write it here, the gradient of R also. Corollary. Gradient of FR, gradient of FR, cross product of R vector equal to 0 vector. Definitely it will be like this. Now, gradient of FR cross R vector equal to, it will be F dash R by R, it will be F dash R by R, R vector cross R vector. You may write like this. Since M A vector cross B vector equal to M A cross B. In vector algebra we have applied this one. M A vector cross this equal to, it is nothing but 0 vector. This is equal to 0 vector. 0 vector. Since the product of two equal vectors is equal to a 0 vectors. Therefore, R vector cross R vector will be equal to 0 vector. R vector cross R vector equal to 0 vector. Very easy. Perhaps you have understood this. Now, gradient of R to the power m, gradient of R to the power m, this is equal to I cap delta delta x of R to the power m plus j cap delta delta y of R to the power m plus k cap delta delta z of R to the power m. This is equal to I cap n R to the power n minus 1 delta R by delta x plus j cap n R to the power n minus 1 delta R by delta y plus k cap n R to the power n minus 1 delta R by delta z. This is equal to n R to the power n minus 1 I cap delta R by delta x plus j cap delta R by delta y plus k cap delta R by delta z. X by R, y by R, z by R. You may write like this. This is equal to n R to the power n minus 2 x I cap plus y j cap plus z k cap. This is equal to n R to the power n minus 2 R vector. R vector. The result of gradient of R to the power n equal to n R to the power n minus 2 R vector. N R to the power n minus 2 R vector. And it is given R, the magnitude of the vector R vector equal to R, and R vector is equal to x I cap plus y j cap plus z k cap. In this case, delta R by delta x is equal to x by R, delta R by delta y by R, and delta R by delta z is equal to z by R. Right? Prove that. Now I am going to prove one thing. Prove that. Gradient of R vector dot A vector. This is equal to A vector. Number 1. Number 2. Gradient of R vector A vector B vector. The scalar triple product of this equal to A cross B. Now prove that gradient of R vector dot A vector. Dot A vector. It is dot. It is not comma, it is dot. Gradient of R vector dot A vector equal to A vector. Where A and B are constant vectors. Where A and B are constant vectors. B are constant vectors. Where A and B are constant vectors. I am going to prove this one. A and B are constant vectors. Now, let A vector equal to A1 I cap, A2 j cap plus A3 k cap. Constant vectors. A1, A2, A3 are scalars, also constant. R vector is equal to X I cap plus Y j cap plus Z k cap. Therefore, R vector dot A vector will be equal to X I cap plus Y j cap plus Z k cap dot A1 I cap plus A2 j cap plus A3 k cap plus A3 k cap. It will be like this. This is equal to X A1 plus Y A2 plus Z A3, the dot product, since it is dot product. X I cap, X A1, Y A2, Z A3, since it is dot product. Therefore, gradient of R vector dot A vector equal to I cap delta delta X plus J cap delta delta Y plus K cap delta delta Z of X A1 plus, it must be scalar, gradient of a scalar function. You will have to find the gradient of a scalar function. It must be scalar. R vector dot a vector. The dot product of the vector function is a vector is a scalar. You always find a gradient of a scalar function. Mind me. Z A3. This is equal to I cap delta delta X of X A1 plus Y A2 plus Z A3 plus Z cap Z A3 plus K cap. This is equal to I cap with respect to X partially differentiation. It will be A1. Others will be 0 plus J cap. 0 plus A2 plus 0 plus K cap. 0 plus 0 plus A3. This is equal to A1 I cap plus A2 j cap plus A3 k cap. This is equal to A vector. This is equal to A vector. Thus, gradient of R vector dot A vector equal to A vector. This means that gradient of R vector dot a constant vector, this is equal to, the result will be the constant vector. Now, R vector, A vector, B vector, it is the scalar triple product of three vectors. This can be written as R vector dot A cross B. You may write like this. You may write like this. A vector, now A vector cross B vector. Now A cross B is a constant vector. Is a constant vector. Therefore, gradient of R vector, A vector, B vector, the scalar triple product of this. This is equal to gradient of R vector dot a constant vector. R vector dot a constant vector. This is equal to the constant vector by number 1. Using number 1, gradient of R vector dot a constant vector. This is equal to the constant vector by number 1. By 1. by 1, you will get this one. All things are very easy. Very easy. Let us take some more problems. Let us take some more problems. I will write problems in this side, then let us take some more problems. Let us try to solve these problems. Let us try to solve these problems. Number 1. A vector and B vector are given. Find the value of the partial differentiation, delta square, second order partial differentiation. Second order. First, you will have to differentiate partially with respect to y of A vector cross B vector. Then, this result will have to be differentiated with respect to x. This is the question. For that, first we have to find A cross B. We have to find A cross B. Solution number 1. Solution number 1. A cross B. The cross product of two vectors. A cross B. Cross product of two vectors. You will have to write here I cap, j cap, k cap. The coefficient of I cap A vector x square y z. Carefully write minus twice x z cube x z square and here twice z y minus x square right. Yes, this is equal to I cap this into this minus this into this, right? This into this minus this into this. This into this means 2 times of x cube z cube minus xy z square I cap. This into this minus this into this. For z cap, remove this one. For z cap, this into this minus this into this. For z cap, this into this means twice x z cube minus this into this, it will be plus x to the power 4 y z. Plus k cap, this into this x square y square z minus this into this, it will be plus twice 2 to 4 x z to the power 4 k cap. This minus this. We have done no mistake, I think. Now, therefore, delta first time differentiating with respect to y. Differentiate A cross B equal to this. Differentiate this with respect to y. Differentiate with respect to y. It will be 0 minus x z square I cap plus with respect to y it is 0 plus x to the power 4z j cap plus with respect to y it will be twice x square yz plus 0 k cap, right? This is equal to minus x z square I cap plus x to the power 4 z j cap plus twice x square yz k cap. You will get this one. Therefore, delta x delta y equal to delta x of A cross B equal to delta x of del y of A cross B. This is equal to with respect to x partially differentiate x z square I cap plus x to the power 4 z j cap plus twice x square y z k cap. This is equal to with respect to x partially, it will be minus z square I cap with respect to x plus 4x cube z cap with respect to x partially plus 4x yz k cap. We have got this one. At the point 102, putting x is equal to 1, y is equal to 0, z is equal to minus 2. We get minus 2. Suppose this is Roman 1 like this. In 1 we get delta 2, delta x, delta y, a cross b at 1, 0, minus 2. At 1, 0, minus 2. Which is 1, 0, minus 2. Therefore, can I remove this one? Just this means we get nan at nan, which is equal to minus of minus 2 whole square I cap plus 4. It is 1 cube. 1 cube. It is minus 2. Z cap, it will be plus 4. X means 1, y means 0, z means minus 2 k cap. This is equal to, it is 4. Minus 4 I cap minus 8 z cap. This is the answer. Answer is minus 4 I cap minus 8 z cap. We have done number 1. We have done number 1. Answer is minus 4 I cap minus 8 z cap. This is the answer. This is the answer. We have done number 1. Now number 2. Come to number 2. Gradient. We have to find the gradient at the point 1 minus 2 and minus 1. At the point 1 minus 2 and minus 1. For gradient, you may write f of x, y, z thrice x square y minus y cube z square. Therefore, delta f by delta x equal to delta delta x of thrice x square y minus y cube z square, which is equal to 6xy, simply 6xy. Delta f by delta y will be equal to, with respect to y differentiation, thrice x square minus thrice y square z square. It is delta f by delta z, with respect to z, it is 0 minus twice y cube z. Minus twice y cube z. Y cube z. Therefore, gradient of f equal to I cap delta f by delta x z cap delta f by delta y plus k cap delta f by delta z. This is equal to this one, 6xy I cap plus thrice x square minus thrice x square minus thrice y square z square z cap plus minus twice y cube z k cap. Therefore, gradient is at the point 1 minus 2 and minus 1. Therefore, gradient f at 1 minus 2 minus 1 at point 1 minus 2 minus 1 is equal to 6 1 minus 2 I cap plus 3 1 square minus 3 minus 2 whole square into minus 1 whole square j cap, right, plus minus 2 for y you will have to write minus 2 whole cube and minus 1 k, minus 1 k. This is equal to 6 into 2 minus 12 I cap, it will be 3, it will be plus 1, it will be plus 4, it will be minus 12 plus 3 minus 12 means minus 9 j cap. It will be minus minus plus 2 and minus 8. 2 minus 8 means minus 16 k cap. It will be like this. Answer is this. We have done number 2 also. The answer of 2 is minus 12 I cap, minus 9 j cap, minus 16 k cap. This is the answer. We have done number 2. Number 3. What is 3? We have to find the gradient of fxy. Gradient of f equal to I cap delta f by delta x j cap. Number 3. Delta f by delta y plus k cap delta f by delta z. This is equal to I cap delta x of the f is x square y plus y cube plus j cap delta y of x square y plus y cube plus k cap delta z of x square y plus y cube. This is equal to, with respect to x partial, differentiate this with respect to x, it will be twice xy. Twice xy I cap. It will be with respect to y, x square plus thrice y square. X square plus thrice y square z cap. And it will be 0. With respect to z, it will be 0. This is the answer. Gradient of f will be equal to 0. We have done number 3 also. Number 3. We have done number 3. Very simple questions. I am going to prove number 4. Number 4. Now let us try to prove number 4. A vector late number 4. A vector equal to A1 I cap, A2 j cap plus A3 k cap. Also R is obvious, x I cap plus y j cap plus z cap. Therefore A vector dot nebula equal to A1 I cap plus A2 j cap plus A3 k cap dot I cap delta h j cap delta y plus k cap delta z. The dot product, it is the dot product. Since it is dot product, therefore you will get A1 delta h plus A2 delta y plus A3 delta z. Therefore R vector. Therefore A dot nebula R vector will be equal to A1 delta x plus A2 delta y plus A3 delta z of, it is vector R vector. This is equal to A1 delta r vector by delta x, a2 delta r vector by delta y plus a3 delta r vector by delta z. That is a vector dot nabla r vector equal to that. Now suppose this is number 1. Now r vector equal to xi cap plus yj cap plus zk cap. Therefore, delta r vector by delta x equal to delta x of xi cap plus yj cap plus zk cap. This is equal to, with respect to x partial differentiation, it is I cap. It will be 0, since we are differentiating partially with respect to x. Similarly, delta r vector by delta y equal to delta y of xi cap, yj cap, zk cap. This is equal to, simply it will be z cap. This will be 0, this will be 0. And delta r vector by delta z will be equal to, with respect to z differentiation, this is 0, it is k cap. It will be k cap. Therefore, from 1 you will get. Therefore, 1 implies. From 1 you will get a vector dot nabla r vector. This is equal to a1 delta r vector by delta x, a2 delta r vector by delta y, a3 delta r vector by delta z. This is equal to a1, it is I cap plus a2 j cap plus a3 k cap. This is equal to a vector. We have proved number 4. Now try to prove number 5. Now number 5. Let this one. A vector is equal to a1 I cap. Therefore, a vector dot nabla a1 I cap plus a2 j cap plus a3 k cap dot I cap delta x, j cap delta y plus k cap delta z. This is equal to a1 del x, a2 del y plus a3 del z. You will get this. Therefore, a vector dot nabla phi equal to a1 del x, a2 del y plus a3 delta z of phi. This means a vector dot nabla phi will be equal to a1 delta phi by delta x, a2 delta phi by delta y plus a3 delta phi by delta z. A to the atomic number. Again, 1. For question number 5, you have given it as number. Now, a vector dot gradient of phi will be equal to a1 I cap, a2 j cap, a3 k cap dot delta phi by delta x I cap plus delta phi by delta y j cap plus delta phi by delta z k cap. You will get this one. because gradient of phi equal to this. Now dot product of this equal to A1 into this, A1 into delta phi by delta H plus A2 delta phi by delta Y plus A3 delta phi by delta Z. A vector dot nebula phi. Therefore, A vector dot nebula phi. Suppose this is number 2. The right sides of 1 and 2 are same. The right sides of 1 and 2 are same. Therefore, from 1 and 2, therefore from 1 and 2, from 1 and 2, A vector dot nebula equal to A vector dot the gradient of phi. A vector dot gradient of phi. We have proved number 5 also. Proved. We have proved number 5. Right? Very easy. These things are very easy. Number 6. Now I am going to prove number 6. Number 6. Number 6. Prove that gradient of phi dot dr vector. This is equal to I cap delta phi by delta x, j cap delta phi by delta y plus k cap delta phi by delta j dot. It is nothing but dx I cap plus dy j cap plus dz k cap. Since our vector is equal to x I cap plus y j cap plus z k cap, therefore dr vector equal to dx I cap plus dy j cap plus dz k cap. dz k cap. dz k cap. From this is equal to dot product delta phi by delta x dx, delta phi by delta x plus delta phi by delta y dy plus delta phi by delta z dz. This is nothing but d phi. This is nothing but d phi. We have proved number 6. We have proved number 6. This is nothing but d phi. The 6 has also been proved. Now come to number 7. You may write here left hand side and it is equal to right hand side. Number 7, we have proved so many times such type of questions. Number 7, the gradient of r to the power minus 3. This is equal to I cap delta delta x of r to the power minus 3 plus j cap delta delta y of r to the power minus 3 plus k cap delta delta z of r to the power minus 3. This is equal to minus 3 r to the power minus 4 delta r by delta x plus, you may write this is equal to I cap j cap minus 3 r to the power minus 4 delta r by delta y plus k cap minus 3 r to the power minus 4 delta r by delta z, delta r by delta z. Now take minus 3 r to the power minus 4 common, r to the power minus 4 common, you will get I cap delta r by delta x plus j cap delta r by delta y plus k cap delta r by delta z plus k cap delta r by delta z. The gradient of r to the power minus 3 is equal to this. Now r vector is equal to x I cap plus y j cap z k cap. R vector modulus equal to r, then r equal to root over x square plus y square plus z square. R square equal to x square plus y square plus z square. This means twice r delta r by delta x is equal to twice x. This means del r by del x equal to x divided by r. X divided by r. X divided by r. Similarly, delta r by delta y equal to y divided by r. Delta r by delta z equal to z divided by r. Z divided by r. It is gradient of r to the power minus 3. Suppose it is number 1. It is number 1. Therefore, 1 implies gradient of r to the power minus 3. This is equal to minus 3 r to the power minus 4. It will be I cap x by r plus j cap y by r plus k cap z by r. It will be like this. This is equal to minus 3. This r will be 1 by r is common. Then it will be r to the power minus 5. Minus 3 r to the power minus 5 x I cap plus y j cap plus z k cap. This is equal to minus 3 r to the power minus 5 r factor. Minus 3 r to the power 5 minus 5 r factor. It has been put. Last one is the r. Last one. Now come to the last one. Come to the last one. Gradient of 8. Gradient of 1 by r. This is equal to I cap delta delta x of 1 by r plus j cap delta delta y of 1 by r plus k cap delta delta z of 1 by r. I cap minus r to the power minus 2 delta r by delta x plus j cap minus r to the power minus 2 delta r by delta x plus k cap minus r to the power minus 2 delta it is delta r by delta y. It is delta r by delta y. It is delta r by delta z. This is equal to minus r to the power minus 2 common. You will get I cap delta r by delta x plus j cap delta r by, this is not factor, sorry, delta y plus k cap delta r by delta z. You will get this. This is equal to minus r to the power minus 2 I cap x by r plus j cap y by r plus k cap z by r. You may write in this way. Since r vector modulus equal to r equal to mod of x I cap z k cap. Therefore, r square is equal to x square plus y square plus z square. This means delta r by delta x. Twice r del r by del x equal to twice x. This means delta r by delta x. Delta r by delta x equal to x by r, etc. Similarly, for the other terms, this is equal to minus r to the power minus 3 x I cap y j cap z k cap. This is equal to minus r to the power minus 3 r vector. R vector. Therefore, A vector dot gradient of 1 by r. This is equal to A vector dot. It is minus 1 by r cube r vector. This is equal to minus 1 by r cube. A vector dot r vector, you may write in this way, because A vector dot mb vector, m is a scalar, small a vector, small b vector are vectors, then it will be m, can be taken outside this, and you may write in this way. From vector algebra we have got this, and we have applied here this. It is nothing but this one, proved. It has been proved. It has been proved. 8 has also been proved. Let us take two very simple problems also. After that I will complete the class. Let us try to solve this problem. F vector is given. We have to prove that F vector is equal to R vector cross gradient of F. Number 1, we have R vector equal to x I cap plus y j cap plus z k cap. Gradient of F vector, gradient of F equal to I cap delta F by delta x plus j cap delta F by delta y plus k cap delta F by delta z, Therefore, R vector cross the gradient of F equal to I cap, j cap, k cap. It is x, y, z, delta F by delta x, del F by del y, del F by del z. The determinant of this. This is equal to this into this minus this into this. You may write y delta F by delta z minus z delta F by delta y I cap plus for j cap z delta F by delta x minus x delta F by delta z j cap plus x delta F, this into this minus this into this, x delta F by delta y minus y delta F by delta x k cap. You see F delta F by delta z, this one I cap plus z, this one j cap plus x delta F by delta. This is nothing but F vector. Proved. Number 1 has been proved. We have proved number 1. Proved number 1. Number 2. Now let us try to prove number 2. R vector cross this equal to F vector. Number 1 has been proved. Number 2. Number 2. F vector dot R vector. This is equal to y delta F by delta z minus z delta F by delta y I cap plus z delta F by delta x minus x delta F by delta z j cap plus x delta F by delta y minus y delta F by delta x k cap. Therefore, this dot R vector x I y j cap plus z k cap. This vector dot of this dot, you may write here also dot. This dot this is equal to x into y delta f by delta z minus z delta f by delta y plus y into z delta f by delta x minus x delta f by delta z plus z x del f by del y minus y del f by del x. This is equal to xy delta f by delta z minus zx delta f by delta y plus yz delta f by delta x minus xy delta f by delta z plus zx delta f by delta y minus yz delta f by delta x. xy delta f by delta z minus xy delta f by delta z minus zx delta f by delta y plus yz minus yz. This is equal to 0. Proved. It is very simple. Proved. Number 3. Proved. Just note it down. Proved. After that, number 3. We are going to prove number 3. Number 3. F factor dot gradient of R f. Gradient of f. F factor dot gradient of f. This is equal to number 3. After 2, this is number 3. Gradient of f. This f vector dot delta f by delta x I cap delta f by delta y j cap plus delta f by delta z k cap. Dot product of this. This is equal to this y delta f by delta z minus z del f by del y delta f by delta x plus this into this z delta f by delta x minus x del f by del z into delta f by delta y plus this into this x del f by del y minus y del f by del x delta f by delta z. You see y delta f by delta z delta f by delta z delta x y delta f by delta z delta f by delta x into y delta f by delta x delta f by delta z. 1 plus 1 minus will be cancelled. It is minus z delta f by delta y delta f by delta x. Here you see minus z, it is plus z delta f by delta x delta f by delta y will be cancelled. And the other terms, this delta f by delta x, these two terms will be cancelled. And also you may write like this also f delta f by delta z delta f by delta x minus z del f by del x del f by del y plus z del f by del x del f by del y minus x del f by del y del f by del z. And these two terms will be also cancelled like this. Plus x del f by del y del f by del z minus y del f by del z del f by del x. You see, these two terms will be cancelled. These two terms will be cancelled. These two terms will be cancelled. Will be equal to 0. Here also you may write this will be equal to 0. The third one has also been proved. This has been proved. This was proved, and this also has been proved. We have proved number 1. The number 1 has been completely proved. Number 2, phi equal to thrice r square minus r to the power half plus 6 r to the power minus 1 by 3. Therefore, gradient of phi equal to I cap delta delta x of thrice r square minus r to the power half plus 6 r to the power minus 3 plus j cap delta delta y of thrice r square minus 4 r to the power half plus 6 r to the power minus 1 by 3 plus k cap delta delta 0 thrice r square minus 4 r to the power half plus 6 r to the power minus 1 by 3. Minus 1 by 3. This is equal to 6r delta r by delta x. It will be common. We shall take it common. 6r minus 4 into 1 by 2 r to the power half minus 1 means minus half plus 6 into minus 1 by 3 r to the power minus 1 by 3 minus 4 by 3 delta r by delta x I cap plus same thing 6r minus 4 1 by 2 r to the power minus half plus 6 minus 1 by 3 r to the power minus 4 by 3 it will be delta r by delta y j cap plus it will be 6r minus 4 1 by 2 r to the power minus 1 by 2 plus 6 minus 1 by 3 r to the power minus 4 by 3 delta r by delta z k cap like this. Now take this common. This is equal to 6r minus 2 times of r to the power minus half minus 2 times of r to the power minus 4 by 3. It will be common. It will be delta r by delta x I cap. Delta r by delta z k cap. Like this. Now you see it is gradient of phi. Gradient of phi equal to this. You may write it as number 1. Now r square equal to x square plus y square plus z square. Now, since r vector modulus equal to r and r vector is equal to x I cap, y j cap plus z k cap. Therefore, twice r del r by del x equal to twice x. This means del r by del x equal to x by r. Similarly, del r by del y equal to y by r, del r by del z equal to z by r. Similarly, it will be z by r. Therefore, 1 implies. From 1, you will get the gradient of phi equal to 6r minus twice r to the power minus 2 minus twice r to the power minus 4 by 3. It will be x by r I cap plus y by r j cap plus z by r k cap. It will be like this. Now, let me write here. This is equal to, the r can be taken outside, r is common, 1 by r is common. Therefore, you will get, this means gradient of phi equal to 6 minus 2 times of r to the power minus half minus 1 minus 2 times of r to the power minus 4 by 3 minus 1 into x I cap y j cap plus z k cap. This. this is equal to 6 minus 2 times of r to the power minus 3 by 2, r to the power minus 7 by 3, it is r vector. You may write 2 common, 3 minus r to the power minus 3 by 2, minus r to the power minus it should have been 7, not 7 by 2, it should have been 7 by 3. Minus 1 by 3, or number one thing, minus 1 by 3. R to the power minus 1 by 3 minus 1 means minus 4 by 3. Yes, we have written minus 4 by 3. Minus 4 by 3 and minus 4 by 3. Minus 4 by 3 minus 1. Minus 4 minus 7 by 3. It should be 3. Correct it as r to the power in the question. Not in the answer, in the question it should have been minus 7 by 3. Minus 7 by 3. 7 by 3. R vector. Proved. This proves this. Yes, we have proved this. Dear students, in the next class, most probably we shall discuss about divergence and curl. Divergence of a vector function. You should always remember that gradient of a scalar function is a vector function, but divergence of a vector function will be always a scalar function, and the curl of a vector function is again a vector function. In the next class, we shall discuss about divergence and curl of vector functions. Today I want to stop here. Thanks for attending the class. Thank you very much.